Okay, welcome back. And in today's lecture, we want to talk about digital input and output. We're going to concentrate on digital output. And what that does is these different pins can be turned into the equivalent of the power rails, the power and ground rails here. The power and ground rails, the power rail is set to 3.3 volts and ground to 0 volts. We can make an individual pin go high or go low, 3.3 volts or 0 volts. And the purpose of that is that we can do things that are best exemplified by using LEDs. I can make an LED turn on or off in code. So before we get to talking about digital input-output, first want to talk about LEDs and simple circuits. So I have an LED here. Pick it up so you can see it. And an LED is a one-way device. It only lets current flow through it one way. And when current does flow through it, it lights up. Let's see what happens when we plug this in. Now, I'm looking for the right edge for this. All LEDs are a little different. But if I plug this in, you can see that the current is flowing through it. If I take it out and reverse it and plug it back in to ground, you don't see anything. Right? LEDs are one-way devices. They only let current through in the proper direction. What's the proper direction? Well, for an LED circuit, we're starting with high up here, 3.3 volts, going through a resistor, and then through the LED to ground. That's the type of circuit we're talking about. We talk about conventional current when we go from high to low. The electrons actually flow in the other direction. Okay, so I have this here, and so what we've just learned is that LEDs are two-way devices. But the brightness of the LED is controlled by the resistor. This is a 220 ohm resistor. Over here I have a 10,000 ohm resistor. I'm going to take this and plug this in over here. And it might look to you like it's off. That's because we're in a bright room. I'm going to hit pause, turn off the lights, and I think you'll see that it's actually glowing, but very faintly. So back again. Let's see if I can show you that it actually is glowing by taking one end. Out and back in. Try to get to go back in. So as I interrupt it, you can see that's going in and out. So there is some light, it's just not very bright. Okay. Here's a different sort of LED. It looks whitish, but the reason why this is whitish is it's actually got two LEDs inside it. One's a green LED and one's a red LED. And the purpose of this is that they're connected in parallel to one another, so that when I plug this in, make sure I get all the power going, connected to the wrong hole here. Right? Current is going through this one way, and it's green. If I take the LED out and flip it, now it's red. So a two-color LED is just two one-color LEDs in opposite directions. So you could use something like this to tell which way the direction of current is going. Okay. In the time that I pause this, I've put in the circuit. There's a little program here. And one of the things that it does is it takes pin 15 and turns it high. And I've connected a resistor and an LED to ground. So of course the LED lights up. Over here, I'm using 2 pins. I'm using pin 11 and pin 14. And the thing about this, you'll see, is that I've got 2 LEDs in parallel, and then there's a series resistor. And the 2 colors are alternating. Okay? So these are effectively a 2-color or a bicolor LED. As a matter of fact, let's take them out and put in my bicolor LED. So that you can see you have the same behavior. We're getting 2 different colors here. Red and probably what looks more whitish to you, but looks green to me. Right? So with something like a bicolor, one button would only give me 1 color, but by having 2 pins, I can play with those pins. I can make 1 pin high and 1 pin low. The current will flow from high to low, turn on 1 color. Then I can flip which one is high and which one is low. Current goes the opposite way through the LED and the other color comes on. Okay? So what we're going to do in the next section of this video is we'll learn how to program the PIC so that we get these behaviors. Welcome to today's lecture, and we're going to look at digital output. And the simplest thing we do with digital output is we connect LEDs to the PIC and we want to turn them on and off. So we're going to talk about the module that controls that, but we're also going to have to talk about circuits and about LEDs, how they work. Let's start off by talking about circuits. Here are the symbols that we commonly use when we're drawing circuits. This is a power connection, and usually what we're talking about with this circle is a pin on your PIC. This is the ground connection. It could be a pin on your PIC, but normally is one of the blue lines on your breadboard since they're grounded. A straight line is simply a connecting wire. A crooked line like this is the symbol for a resistor. A resistor is a conducting wire, but it's not a good conductor. It has resistance. It has far more resistance than an equivalent amount of straight wire. And this symbol, the little symbol that we have here, is a light emitting diode, usually abbreviated LED. So when we build circuits, we're going to build them using these symbols. So here's a circuit symbol. Here I've connected a pin, and it's connected to the PIC, and the PIC is powered up to 3.3 volts. That's the maximum it can go. Okay? There's a conducting wire to a resistor, conducting wire to ground. Right? So it's plugged into the blue lines on the breadboard. And for the breadboard, the voltage for ground is 0. Now, for a current to flow, for anything to happen in a circuit, you need a conducting path from high to low. Okay? Without that, nothing's going to happen. Okay? And by convention, we talk about the current flowing from high to low. But what actually happens is electrons flow the other way. Okay? That's all right for us. Conventional current's fine. Now, you may recall that in high school, or even earlier, you did Ohm's law that says when you have a voltage difference on either side of something, right, then there's a relationship between the resistance of the wire and the current that flows through it. Okay? Now imagine this was a 220 ohm resistor. the voltage drop or voltage difference across this resistor, well, that's 3.3 on this side, 0 on that. So 3.3 volts divided by 220 ohms. That's going to be 0.015 amps. People don't usually talk about amps in electronic circuits. They usually talk about milliamps. 1 milliamp is 1,000th of an amp. Okay? Generally speaking, there's a limit to how much current you can get out of your PIC. One pin can only deliver about 20 milliamps, and so we wouldn't want to go much smaller than this resistor, because then the current would start to exceed 20. Here's another circuit, but this time we've made it a little more complicated. I've thrown in a besides the resistor, I've thrown in an LED into the mix. So here are some pictures of typical LEDs, right? All different shapes, different brightnesses too, right? And different colors. Some even are not visible lights. Some will be infrared. We'll play with infrared LEDs as well. And there are also LEDs that that are red in one direction or green the other. They're called bicolor LEDs. Now, LEDs are one-way devices. If you see this side here, conventional current cannot flow through an LED this way. If you put it in a circuit backwards, it just doesn't light up. Okay? So conventional current goes through an LED in only one direction, okay? For the light up. If it's not lighting up, usually you have it in backwards. And when you do it, LEDs always have a voltage drop when they're shining of about 2 volts. That voltage drop over the LED is usually called V forward. Okay? So this was 0, but now this is 2 volts. This is 3.3 volts. So the difference here is shrunk. So the voltage drop over the resistor is now about 1.3 volts. Okay? And as I mentioned, the maximum current from a digital pin, it's about 20 milliamps. So you need to keep this resistor big enough such that the current stays under milliamps. That resistor is called a buffer resistor because it buffers how much current you're getting out. It has to be at least 65 ohms. Something like 100, 200, that'll be fine. 1,000 ohms will be fine, just as long as it's bigger than 65. Hopefully, you'd probably want to be much bigger, so 100 is probably the minimum that you'd use. Now here's that circuit again blowing up. Right? From Ohm's law, we know that if I keep increasing this resistance here, then the current goes down. Okay? What effect does that have on the LED? Well, LED brightness is given by power equal to the current through it times the voltage over it. But the voltage is fixed at 2 volts. So the thing that determines the brightness of the LED is how much current is going into it. So if you increase R, you're decreasing the brightness of the LED. Let's talk a little about bicolor LEDs. These are simply 2 LEDs in the same little plastic cover. Usually the cover is transparent, not red or green or yellow, simply because you don't want to change the color of the light you get out. Okay? So the 2 LEDs are in the circuit, but they're in different direction. And to make one light up, one color show as opposed to the other color, you're going to need 2 pins, 2 digital pins on your PIC to control which color you see. So in this setup, I've drawn the bicolor LED as 2 separate LEDs connected in parallel. And that's actually what it is. It's just the package is so small you can't see them. So if this pin is high and this pin is low, that's this guy here and here, right? Then when the current goes through the resistor, there's two possible paths. It can't go through the red LED because it's got the wrong orientation. It can only go through the green LED. So the green LED lights up and it glows green. If I flip the polarity of the pins, whether it's high or low, right? So now this one's high, this one's low. As the conventional current comes out, there's two possible paths, but the green LED is oriented backwards, so no current can flow through it that way. So all the current flows through the red LED back to the other pin, and the red LED glows. Should mention that if you take these two pins and you toggle them back and forth very quickly, you can actually make the LED to appear to be a third color. Right? If you flash green, then red, then green, then red really fast, your eye is going to see some sort of yellowish, orange, pinkish color, right? Depending on how fast you flash it. Okay, so that's all we need to know about circuits and LEDs. Now we got to go back and talk about the PIC itself. And here's a picture of our PIC. And now we're finally really getting to talk about all our pins. Okay, and the first thing you see when you look at all the pins is my numbering is screwed up. And should be from 1 down to 14. And over here, each of these pins has a bunch of different names. That's because of something called multiplexing. Each pin on the PIC tends to do many different things, except a few special ones. This one, the master clear, that's a programming pin, an important programming pin. So that's all it does. VSS, that's a ground connection. Here's another ground connection. This guy is also another ground connection. And these are power connections. These are not programming pins, right? So we're never going to get to program them. They're how we connect up to things on the board. A lot of those connections are done on the microstick 2 for us. The pins we get to work with are all these other ones. So it would be 2 down to here, 14, 15 back up. Okay. Now, the pins that we're looking for, the digital pins, have names like RA0, RB15. This diagram is kind of complicated to see what we want to see. So let's go down to the next page. The next page, all I'm showing are the digital pins. Okay? And so they have names like RA0, RA1, then there's RB0, B1, B2, B3, right? So all the pins, other than the ones that are marked with X's, those are not control pins. Those are for programming and power and ground. So we don't ever get to use them. All the other pins in this package, in fact, are digital pins. Well, can be digital pins if we program them appropriately. Now you see that they have names like A or B, but, right? And we talk about these pins as collections, and we call them either port A or port B. In this package, port A only has 4 pins, port B only has 16 pins. Depending on the package you buy, like this is a 28-pin PIC, you could buy a version of this with 44 pins. There'd be more port A pins. There could even be a port C or a port D, depending on which PIC you buy. So we talk about the groups of pins as ports, right? So port A and port B. So port A 0 pin, port A, pin 1. Now, to use these pins, there's a number of functions in the plib legacy peripheral library. Okay. The first function is super important. If we want to use these pins as digital output and they're multiplexed with all these other things, then we've got to set the pins to be digital output. I'll explain what port and pins means a little later. Okay, so this is the first and most important function, the one that actually makes a pin a digital output. Once they're digital outputs, you can either set the bit, remember in computer terminology, set means set to high, right? So turn it to 3.3 volts, right? And clear means set it to 0, right? So set bits is the command we would use to turn a pin on, and clear would be to turn it off. There's an extra function in there called port toggle bits, which is really cool because what it does is every time you call it, the bit for whatever pin you call it, if the pin was on, it turns it off, but if it was off, it turns it on. So it toggles between the states every time you call it. Okay. Lastly, there's this function called port read bits, and because it's a read, you read into some value, right? And we'll talk more about value in a second. Okay, what is port? Well, there's only two possibilities. You're either talking about port A or port B, and so this is a special language that the plib library understands to know that you're talking about port A, so IO port underscore A or IO port underscore B. Okay? And when you talk about pins, you talk about their last numbers. So bit 0, bit 1, all the way up to bit 15 if you in port B. And you can, under pins, you can put a bunch of them together and do the operation all at once by using OR statements. For instance, if I took port B and put it here, IO port underscore B, and then bit 0, bit 1, and bit 4, put it up here, then RB0, RB1, and RB4 would be set as digital output pins. Should I talk about this guy a little? Well, value is a number that depends on which bits are set. And it's going to be easiest to read value as a binary number because in port B there'd be up to 16 pins. Then in the 16 bits, as you read them, there'd be either zeros or ones for whether the bits would be set or not, that is turned on. Let's now look at some code. Okay, so here's my program. And to do the breadboard like that little video with the flashing LEDs at the start, here's the code we would need. So we're in main, configured the UART, cleared the screen. I'll print some messages later. And here I have port set digital out, port B, and I'm doing 4, 5, and 6. Right? So 4, 5, and 6 would be pin 11, pin 14, and pin 15. Okay, so this statement configures RB4, RB5, RB6 as digital outputs. Port set bits in port B, so RB4 and RB6, they're set to high. Port clear bits, so RB5, that's set low. Okay, so these statements are enough to turn on the pin, the LED that's connected to this pin to ground, because this guy's set to high, so it comes on. And what I've done is 4 has been turned on and RB5 is turned off. So the LED is set one way. But I wanted that bicolor LED to blink. So if I go to my code, what I've done inside the while loop, and for the first time inside the while loop, we're getting the while loop to do different actions. Okay? So in here, what we've got is port toggle bits, and I toggle the two pins on the same side of the PIC, right? So RB4 and RB5. And so one of them's on, one's off, so when I toggle, they flip on and off. I want to check that, so I'm going to read the value of those 2 bits, right? And as I said, right, it's easier to read the binary value. So here I have if value equals, or double equals, right? So is it equivalent to 0B1000000, right? 0 bit, 1 bit, 2 bit, 3 bit, 4 bit, 5 bit. So bit 5 is bit 5 on. So then RB5 is high, right? Bit 4 is low because it's 0. This one is just the opposite, is bit 5 off and bit 4 on. And those are just little messages to show me what's going on. And here, right, is a delay. It's just a long for loop, 300,000 loops, right? That creates a very simple delay, nothing very fancy. And to show you how this is working, now with the lights, I want to show you the printout for this function. So in PuTTY, you can see it's switching the pins between high and low, blinking the LEDs. Okay. So as you can see, actually controlling LEDs is actually fairly straightforward. Bye for now.